recording, and I think I'm going to get started with this. And I'm going to discuss how to do this problem. Number one, if you get it on a final exam as a multiple choice, I'm going to do that way first. And then I'm going to go back and say, what if you didn't get it as a multiple choice? What if you didn't have the answers in front of you? How do you do this as an open-ended question? So let's first discuss what would happen if we wanted to do this example. And it's a multiple choice example, and it's a radical equation. And if you recall what I said about radical equations is that once you do a radical equation, you always have to check your answer. It is possible to do everything correct, and yet when you work it out, your answer or answers do not work out. You might get what's called an extraneous root. So here's what I'm going to do. If I had this as a multiple choice question, I'm looking at it and I see that the answers they give me really only gave me two choices. One choice is x equal to -1, and one choice is x equal to 6, because the first choice is both of them. The second choice is only -1. The third choice is just 6. And the last choice is no answer. I'm going to just check these two numbers. If they both work, I'll pick A. If only -1 works, I'll pick B. If only if 6 works, I'll pick C. And if neither of them work, I don't have a choice. The answer has to be no solution, because that's the only possible other answer. So checking x equal to -1, I'm going to replace the x with -1, and this will give me the square root of -1 plus 10 plus 2 equals -1. I replace the x with -1. Well, -1 plus 10 is 9, so this is the square root of 9 plus 2 equals -1. And I know that the square root of 9 happens to be 3, so I get 3 plus 2 equals -1. But 3 plus 2 equals 5. These two are not equal. In other words, this answer is no good. So if you notice it, this can't work because this has -1 and 6, and this can't work. So it might be just 6 is the answer, or it might be nothing is the answer. So now I'm going to check my answer with 6. Doing the same thing, replacing the x with 6. I'm getting 6 plus 10 inside my radical, plus 2 equals x, which is 6. Now 6 plus 10 is 16. So this is the square root of 16 plus 2 equals 6. And the square root of 16 is 4. So we're getting 4 plus 2 equals 6. And 6 does equal 6. This does work. So the answer -1 did not work. The answer x equals 6 did. So my answer, my choice C, is my correct choice. Notice I didn't solve the question. I just took the solutions and worked with the solutions and see which ones they worked. Well, what if this, and this would be a perfect way to solve or answer a question that's on a multiple choice test. Remember, you want to do things as quickly as possible. You want to make sure that you're doing things efficiently, not spending too much time on a problem, etc. So in a question like this, where you have a radical equation, and you know you must check the answer, because even if you do all the right work, you're going to have to check. You may as well just do the check and see which ones work. So let's go back to this question and see what we would do if This is what we call an open-ended question. It's not a multiple choice. It's an open-ended question, and you have to work it out. Well, if you remember with this radical equation, the first thing you want to do is get the radical by itself. So you're going to subtract 2 from both sides. This is which will give you the square root of x plus 10 equals x minus 2. You want to get the radical all by itself. And then you want to square both sides of your equation, because when you square a radical, it removes the radical. And the whole point is to get an equation that doesn't have a radical. So when I multiply the square root of x plus 10 by itself, when I square this, it obviously just gives me x plus 10. But the side that's not inside the radical actually has to be multiplied by itself. We have to actually do the x minus 2 times the x minus 2, which means that we have to do FOIL. So I get x plus 10 equals x squared. Outer is negative 2x. Inner is negative 2x as well. And last, negative 2 times negative 2 is positive 4. So that gives me that x plus 10 equals x squared minus 4x plus 4. And I see what I have here is a quadratic equation because I have an x squared. And I know when I want to solve quadratic equations, I want to get them equal to 0. And it's easier to remove the things from the left side in this case than from the right. So I'll minus x from both sides. And I'll minus 10 from both sides. So that I end up with 0 over here equals x squared. Negative 4x and negative x is negative 5x. And plus 4 and negative 10 is minus 6. And I have to factor this. All the things that we've learned to do this term, notice every step of what we learned leads on to the next thing that we're learning. Obviously, this is going to be x and x. The last term is negative, means one is positive, one is negative. And I need numbers that multiply to 6, but when I subtract them, they're going to give me 5. 6 and 1 is what works. And since the larger number has to be negative because the middle sign is negative, I put the 6 with a negative and the 1 with a positive. That gives me x plus 1 equals 0. So that gives me x equals negative 1. And this gives me x equals 6. So here are my two answers, negative 1 and 6. Notice if I stopped here and I said my two answers are negative 1 and 6, I'd be wrong. Because after I've done this, I now have to check. I'm not going to check again because I did it before. And if I do the check, I see that negative 1 doesn't work, but 6 does work. So my only answer is 6. Notice for a multiple choice problem, actually working it out doesn't help you because you still have to do the check. So it makes sense if you have it as multiple choice, just do it with a check because it's giving you the possible answers. You're going to have to check if those are the right answers in any case. So this is what we had finished off with on Thursday. Okay, so let's now, unless there's a question, if anybody has a question, I'll stop right here. But if not, let's go on to the next topic, There are two topics that we have to still talk about in chapter 6. One of the things that we talked about during the term has been working with exponents. And we learned all the rules of working with exponents. In other words, when you multiply numbers with the same base, you add the exponents. When you have two numbers in a parentheses with an exponent outside, you have to distribute that exponent to all the things that are inside the parentheses. We worked with them, but the type of exponents we worked with were starting, first of all, just real number, whole number exponents, positive whole numbers. Like I could have started with something like a to the third. In other words, the first type of exponents that we ever talked about were not fractions, they were not decimals, they were not negatives, they were positive whole numbers. And we defined something like a to the third to mean a multiplied by itself 3 times. In other words, the exponent tells you how many times you're multiplying the base, the number that has the exponent. We went from positive whole numbers as exponent to a 0 exponent. We talked about something like a to the 0, and we said anything to the 0 exponent is going to be equal to 1. A million to the 0 exponent, negative 75 to the 0 exponent is 1. 250,000 x to the 4th, y to the 7th, all to the 0 exponent is going to be 1. Anything with an exponent of 0 equals 1. And then we talked about negative exponents. In other words, if I had something like a to the negative 5, and we said what a negative exponent told us to do, obviously you can't multiply a number negative 5 times. That doesn't make sense. What it means is to take the reciprocal. In other words, a to the negative 5 is the same as 1 over a to the positive 5. Take its reciprocal. In other words, put 1 over the number and make the exponent positive. A to the negative 5 means 1 over a times 1 over a times 1 over a times 1 over a times 1 over a. 1 over a multiplied 5 times. And these are the types of exponents we've dealt with until now. And now I want to talk about something called a fractional exponent. Now, the simplest fractional exponent is something like an exponent like a is 1 to the 1/2. 1/2 is probably the simplest fraction we can think of. What does it mean when I say I have a to the 1/2? So think about this. What if I were to multiply a to the 1/2 times a to the 1/2? Well, I know when I multiply, what I do is I add the exponents. So that'll be a to the 1/2 plus 1/2. And I know when I add a half and a half, I get 1, which is a to the 1, or just plain a. In other words, if I multiply a to the 1/2 times a to the 1/2, it gives me a. And I think, where else do I multiply something by itself and gives me a? And that's with the square root. If I do the square root of a times the square root of a, we've talked about this. When you multiply a radical by itself, it just removes the radical. It just gives you plain a. The square root of 25 times the square root of 25 is 25. The square root of 7 times the square root of 7 is 7. Anytime you're multiplying a radical by itself, it gives you what's inside the radical. So if I compare this, I know that a to the 1/2 times a to the 1/2 gives me a. And the square root of a times the square root of a gives me a. So it must mean that a to the 1/2 is the same as the square root of a. And that's exactly how we define it. When we see a 1/2 exponent, that's another way of saying the square root. If I give you a question like this, and I ask you, what is 64 to the 1/2 power? I know that the 1/2 power is the same as doing the square root of 64. So it must mean that it's equal to 8. The 1/2 exponent means the square root. If I give you 81 to the negative 1/2 exponent, well, that's telling me to do two things. I know the negative exponent means take the reciprocal of the base, so put 1 over 81, and change your exponent to positive. So this means 1 over 81 to the 1/2 power. And 81 to the 1/2 power means the square root of 81, which is 9. So this means 1 over 9. In other words, this one exponent of negative 1/2 is telling me to do two things. It's telling me take the reciprocal and also take the square root. So fractional exponents and exponents in general are very efficient because they can tell you to do a bunch of things in one shot, in one example. Okay, so we said the square root is the same as the exponent of 1/2. Now you might also see something like this. 64 to the 1/3 exponent. What does it mean that we want to do 64 to the 1/3 exponent? So the 1/3 is the same as the radical where the index is 3. This is called the third root or cube root of 64. In other words, anytime you see a fractional exponent, it's going to tell you to do the radical. It's going to tell you to do the root, and the number in the denominator of the fraction is what we call the index of the radical. Since this is 1/3, the index is 3. Notice when the exponent is 1/2, the index is 2, but we usually don't write in an index of 2. We just write the square root of 2. That really means the same thing as multiplying something 2 times. The index is 2. So with 1/2, we don't write in the index. With any of the others, we do write in the index. So when I say 64 to the 1/3, I'm talking about this number that multiplied by itself will give me 64. It happens to be equal to 4. You can do this on your calculator. If you want to do 64 to the 1/3 power, what you do is on your calculator, you type in the 64. You then press what's called your exponent button. Now, usually the exponent button looks like a button that has a little arrow going up. And when you're typing, this is also used as the exponent button. If you want to type it, you can type it from your on your, it's on the 6th button. So this is the what's called the exponent button. And then you put parentheses 1 divided by 3. Because the way we get a fraction is to take the 1 and divide it by the 3. Now I'm putting it in a parentheses because otherwise the calculator will think that the only thing you want to do the exponent by is by the 1, and then you're dividing your final answer by 3. So when your exponent is more complex than just a plain single number, you have to put it in parentheses. Now, if I do that, if you have a calculator, you can try it. 64 exponent, parentheses 1 divided by 3, press equal, and of course it comes out to 4. So you can do fractional exponents, which are also radicals, on your calculator if you want. What happens if you have something like this? What if I had something like this? 25 to the negative 1/2 exponent. What would that mean? Well, this exponent is telling me to do two things. The negative is telling me to take the reciprocal, so I'm putting 1 over 25 and making the exponent positive. That's what a negative exponent tells you. Take its reciprocal. This 25 is really over 1. Anything that's written without any fraction means it's over 1. So therefore, I have to put it in the denominator. And the exponent goes from negative 1/2 to positive 1/2. Remembering that the 1/2 exponent means the square root. The square root of 25 is 5. So the answer to this is 1/5. If you would put 25 exponent negative 1 divided by 2, just like we did using you probably would get an answer that says 0.2. In other words, when you do it on your calculator, it will give you a decimal answer rather than a fraction answer. So it's better when you see a negative exponent just to put 1 over it. What if I gave you this? Suppose I said, I want you to figure out what a to the 2/3 exponent means. So until now, all the exponents that I gave you that were fractions had a 1 as the numerator of the fraction. So what does it mean that we want to do 8 to the 2/3? I'm going to first do it without a calculator, and then we're going to use our calculator and try it with our calculator. Actually, the fraction 2/3 really means the fraction 1/3 times 2. Any fraction, let's say 5/7, can be rewritten as 1 over the denominator times the numerator. 5/7 is 1/7 times 5, just like 2/3 is 1/3 times 2. You can break up a fraction into 2 parts. 1 over the denominator times the numerator. So how does that help us? 8 to the 2/3 is the same thing as saying 8 to the 1/3 to the 2 power. Remember, when you have an exponent with a second exponent, it means that you're multiplying the 2 exponents. So 8 to the 2/3 is a combination of doing 8 to the 1/3 and raising that to the 2 power. Now, 8 to the 1/3 means the cube root of 8, which is 2. And what I have to do with that 2 is I have to raise it to the 2 power. So 2 squared gives me 4. And you are correct. I think that was Dominic who gave me that answer. That is totally correct. So you could, of course, have done that on your calculator. How would you have done it on your calculator? By putting in your 8, pressing your exponent button, and then doing parentheses 2 divided by 3. You don't have to do it in 2 steps. And if you do that, it gives you 4 directly. So you can do these problems using your calculator, or you can do them in your head. But again, you have to understand that a fractional exponent tells you to take the square root or the cube root, whatever the denominator is. So what if I gave you a problem like this? I'm going to do one more with you, and then I'm going to give you something to try out. Suppose I gave you (81/25) to the -1/2. What would you be asked to be doing here? Over here. So what would we be asked to do? Well, I'm going to follow all my rules that I know from exponents. Number 1, I know when I have something in parentheses with an exponent on the outside, it means I have to distribute that exponent to everything that's inside the parentheses. So that means 81 to the -1/2 over 25 to the -1/2. Now, if you remember also when we started working with exponents, when we had negative exponents, what we did is we drew our line, and if something had a negative exponent, we moved it. If it was in the numerator, we moved it to the denominator. If it was in the denominator, we moved it to the numerator. So the 81 to the -1/2 is going to become 81 to the 1/2 in the denominator. The 25 to the -1/2 in the denominator, we have to take its reciprocal also because it has a negative exponent. It becomes 25 to the 1/2 in the numerator. So So we can simplify this to get 25 to the +1/2 and 81 to the over 81 to the +1/2. Now remember, the 25 to the 1/2 means take the square root of 25, so that's plain 5. And 81 to the 1/2 means take the square root of 81. The square root of 81 is 9. So my final answer comes out to be 5/9. In other words, we work with fractional exponents exactly the same way we work with regular exponents, using all the regular rules. The only thing we have to remember is that the final step, that a 1/2 exponent means take the square root, a 1/3 exponent means take the cube root. etc. If I gave you a question that looks like this, suppose I gave you 64 to the 1/9 exponent raised to the 3rd exponent. Now, I could do this directly in my calculator. I could put it into my calculator exactly the way you see it here. In other words, I could type in parentheses 64. Now, how do I put in the 1/9 exponent? I have to press my exponent button, which is that little arrow up. Not all calculators have this symbol. So if you're not sure which is your exponent button, you can always send me a picture of your calculator and I'll figure it out for you. But most calculators have a button that looks like this. That means exponent. And I want to do 1/9. And remember, when it's a fraction, I want to put it in parentheses. So I do 1 divided by 9. That takes care of the inside. But I still want to do it to the exponent of 3. So I press my exponent button again, and I just press 3. Now, since 3 is just a plain number, it doesn't have to be in a parentheses. So if you put it in parentheses, it's fine. If you press equal, then you get 4. And that would be your answer. In other words, you could do this totally with your calculator. But let's see if we can figure it out, not with a calculator. Let's see if we can figure it out what it means. Now, I know I have 64 to the 1/9 to the 3. Now, I know when I have two exponents, usually what I do is I multiply the 2 exponents together. So I get 1/9 times 3, because an exponent with an exponent, you're just multiplying the exponent. And 1/9 times 3 is 3/9. And 3/9 is the same as 1/3, it reduces. So this really means 64 to the 1/3 power. And the 1/3 power, remember, we meant it was the 3rd root, or the cube root of 64. What number times itself 3 times is going to give us 64? And the answer is 4. So you could have done it using your calculator and just typing it in into your calculator, or you could have done it, as I said, in your head, figuring out, because the 1/9 times the 3 is really a 1/3 exponent, and a 1/3 exponent means the cube root. Okay, I'm going to give you one to try on your own, and then we're going to go a little further. See if you could do 36 over 100 to the negative 1/2 power. Simplify it. I'll give you a minute or two to try it. And you can do it either using your calculator or just figuring it out in your head. I'm going to take attendance while you're doing that. And I'm going to do this with my, without using calculator. Again, if you do it with a calculator, the likelihood is you get a decimal answer. Now, if you get a decimal answer and it's a multiple choice question, you can take the answers that are listed on the question and change them all to decimals and see which one matches. But I think this is something that we could do without using, referring to the calculator. Again, I distribute that negative 1/2 exponent to both the numerator and the denominator. So it's going to be both the 36 to the negative 1/2 and the 100 to the negative 1/2. Now, a negative exponent means that you have to take its reciprocal. So the 36 to the negative 1/2 is going to go to the denominator as a positive 36 to the 1/2. And the 100 to the negative 1/2 it's in the denominator, it's going to have to come up to the numerator and become 100 to the positive 1/2. When you have a negative exponent, it's telling you to take its reciprocal. So if it's in the numerator, you have to move it to the denominator. If it's in the denominator, you have to move it to the numerator. And now we just have to do the final step of figuring out, what does 100 to the 1/2 mean? And remember that the 1/2 exponent, and you're going to have to remember this because we're going to be using it later on again, the 1/2 exponent is the same as the square root of 100, which means it's 10. And the 36 to the 1/2 is the square root of 36. Again, the 1/2 exponent means the square root, which is 6. So my final answer becomes 10 over 6. You actually could reduce this because the numerator and denominator can both be divided by 2, and your final answer in simplest form would then be 5/3. 10/6 is the correct answer, but it's not reduced. If you wanted, if it's asked for simplest form, you would have had to give 5/3. So that's how we deal with fractional exponents. Okay. Our next thing that we're going to be talking about is a very special number. Okay, so I'm going to erase this.
Hi, Professor. This is Jessica. I wasn't sure if you got me for the attendance because my internet froze.
Okay, let me check that. I think I marked you absent, but I'm going to change it.
Okay.
Yeah, I marked you absent. Okay, Jess, and I was surprised because you're usually here.
Thank you.
Okay, so I'm changing that. Okay, anybody else, let me know if, or any questions, just, I'm glad when I'm interrupted, I mean, preferably about questions about math, but about anything is fine. We're going to talk about a number that is used only occasionally. It's not a real number. It's not a number that's part of our regular numbers on the number line. When we started this chapter, I said, well, if I ask you to do something like the square root of negative 25, our answer was, you can't do that. You can't do it in the regular real number system because the square root of negative 25 means what number times itself will give you negative 25. And that negative is a real problem because I know when I take a positive number and I multiply by itself, my answer is going to be positive. And when I take a negative number multiplied by itself, it also gives me a positive. There's no time in the real number system where we could multiply a number by itself and end up with a negative number. So in the real number system, the square root of negative 25 doesn't exist. But there is another number system, which is called the imaginary number system. And it's not a figment of my imagination. That's why it's not called imaginary, because it really has uses in real life. It's just that the numbers on the number line that we're used to using are called the real numbers. And this is not a real number. So what do I call something that's not real? We'll call it imaginary, even though it's not a figment of my imagination. Okay, in this, there's only one new number in this new set of numbers. That number is something that's indicated by the letter I, the lowercase I. Now notice, I'm not writing the I like this. And I think you probably realize why I don't want to do. It's a lowercase I. If I just put a straight line with a dot on it, it's possible you won't notice the dot. It's not, but if I don't make it big enough, and it's going to look like the number 1. So I will always write the I as a little, like with a little hook, or sometimes I'll write it this way as a script I, so you can distinguish. It's not just going to be, and it's just a matter of the reason I'm writing it that way. And you'll mostly when you see it, that's how it's written. It's written in, it's typed in, it's written in italics, just to make sure that you don't think it's a 1. This number I is defined as the square root of negative 1. Now you know that in the real number system, there's no such number. But in our new number system, it's a new number. And we've added this one new number. And once I've added this one new number, I can take care of all problems that have negative square roots. Because if I have something like, say, like the square root of negative 25, I could break that up into the square root of 25 times the square root of negative 1, because 25 times negative 1 is negative 25. And now this square root of 25 is a regular real number because it doesn't have any negative in it. Square root of 25 is 5. And the square root of negative 1 is our new number I. So that we can talk about the square root of negative 25 as 5i. Obviously, this is not in the real number system because there are no i's in the real number system. But in the imaginary number system, you get this 5i, and yes, you must put in the I, because if you don't, it'll look like your answer is 5, and the square root of negative 25 is not 5. The square root of negative 25 is 5i. In other words, it's a new number, and it only works in this new number system. I can't talk about 5i in the regular, what we call real number system. If we have a number like this. Let's say I have 3 plus 5i. This number is actually a combination of a real number, because 3 is a real number, it doesn't have any I with it, and 5i, which is an imaginary number. Any number that's a combination of a real and imaginary is something called a complex number. So it's as if we took our original set of real numbers and we expanded it to include all these numbers that have i's as well. And then in this new number system, we can deal with square roots of negative numbers. Now, I have to tell you ahead of time that I want you to look in this complex number system, because in a regular everyday problem, you're just going to be dealing with a real number system, and therefore you won't be able to do the square root of a negative number. But if you're allowed to use the complex numbers, then you can answer these type of questions. If you notice, this is something that's called A plus BI form. A complex number is a combination of a real number, that's my A, and an imaginary number, my BI. So this format is called A plus BI form. Notice when we write numbers in this format, the real part goes first, the I part goes second. Now, if I were to have given you something like this, the square root of 16 minus the square root of negative 64. And I asked you to simplify it. Obviously, the square root of 16 would be 4. The square root of negative 64 would be the square root of 64 times the square root of negative 1. And the square root of 64 is 8, so this is minus 8. And the negative 1, the square root gives me I. This cannot be simplified any further because the 4 and the 8i are not like terms. Think of it think of it as 4 minus 8x. You couldn't combine them further with that. So the same thing over here. You cannot make this simpler. Notice this is A plus BI form. Obviously, it's plus a negative 8. So it's 4 plus negative 8i. It's A plus BI form. It is a complex number, a combination of a real number and an imaginary number. You can even take something like this. Let's say I had the square root of negative 50. Now, I know how to simplify just the plain 50. The 50 I could break up into 25 and 2. The negative becomes, that's my negative 1 that goes after it. In other words, when I want to simplify something with a negative inside a radical, I just look at the positive numbers and stick the negative 1 sort of at the end. Now, what does that give me? The square root of 25 doesn't have a negative, so I can write it. It's just plain 5. The square root of 2 is irrational. I just have to leave it the square root of 2. And the square root of negative 1 is I. So the square root of negative 50 is 5 radical 2i. Just as an aside, it's very important that you realize the I is not in the square root. The I is outside the square root. The negative 1 in the square root translates to an I without any radical. What's very often done is that this is written 5i times radical 2. Usually when we're writing things, because handwriting things, not so important when you're typing, but when you're handwriting things, you put the radical at the end because you don't want your pen to slip and it looks like that last number ends up inside the radical. So the better way of writing this, instead of writing 5 radical 2i, it's better to write 5i radical 2. Remember, these are just 3 numbers that you're multiplying. It doesn't matter when you're multiplying what order you put those numbers in. Usually we put the numbers outside the radicals in the beginning and the radical part second. So if you know how to simplify a regular radical, you can simplify something with a that ends up being an I, because the negative, you just put -1 at the end if there's a negative number inside your radical. And that translates into an I outside the radical. Now, just like when we worked with polynomials, when we worked with fractions, when we worked with radicals, we learned to do 4 things. We added, subtracted, multiplied, and divide. I want to show you how to do those 4 operations when we have our complex or imaginary numbers. And they work exactly as you would expect them to work. In other words, you combine like terms. So if I have something like this, the square root of 49 minus the square root of -81 plus the square root of 25 minus the square root of -9. Let's say I gave you something like that. And I told you, I want you to combine this. I want you to simplify it as much as you could and combine all the like terms. Usually the term used would be simplify. Okay, the square root of 49, that's easy. That's just 0.7. Now the square root of -81 is 81 times the square root of -1. And the square root of 81, the positive, is just 9. And the square root of -1 is I. In other words, when I see something like this, the square root of -81, I know I just take the square root of the number, and the minus in the inside translates to an I, not inside the radical. Now, the next thing I see is the square root of 25. So that's just 0.5. There's no negative there. But the square root of -9 is like the -81. It's 9 and -1. So that becomes minus, because this was a minus over here. This minus and this minus are 2 different things. The minus inside the radical translates to an I. The minus on the outside just stays a minus. So this becomes -3i. And now I look at the like terms. The 7 and the 5 don't have any i's next to them, so they can be combined. 7 and 5 is 12. The -9i and the -3i can be combined because they're like terms. That's -12i. So my answer comes out to be 12 minus 12i. Notice this is an A plus BI form. The real part is 12, the imaginary part is the -12i. So, and these cannot be combined because this has an I, but this doesn't. So it's regular algebra. There's nothing too complex about this. So let me give you a problem to try. Okay, so combine this. Here's your question. 3 minus 5i minus 2 plus I. Get this as simple as as simple as you possibly can. Okay, I think we had enough time with this. Remember, when we have a minus in front of a parentheses, it's as if we're multiplying by a -1. So first of all, this just stays 3 minus 5i. This becomes -1 times 2 is -2. And -1 times I is -1i or -i. And all I have to do now is combine the 3 and the -2 are real numbers. That gives us 1. The -5i and the -i is -6i. So my final answer came out to be 1 minus 6i. Notice it is in a plus bi form. What happens when we want to multiply complex numbers? So let's take two complex numbers and try and multiply them. Let's say 3 minus 5i and multiply it by the 2 plus I. Taking the same two complex numbers, instead of subtracting them, I'm now multiplying them. Well, guess what I see? I see two binomials, and I want to multiply the binomials. Remember, I can't simplify these any further because the 3 and the 5i are not like terms. It's like regular algebra. We use FOIL. 3 times 2 is 6. Outer is 3 times I, which is 3i. Inner is -5i times 2, which is -10i. And finally, -5i times I gives me -5i squared. Don't forget, I times I gives us I squared. And I have to make a comment about what I squared is about. Now, if you think about I squared, what it means is obviously I times I, which means it's the square root of -1 times the square root of -1. Because I is the square root of -1. It's just a symbol that we use instead of writing that radical, because there's no way of simplifying this, we just call it I. But think about it. I'm multiplying a radical by itself. And I know anytime I multiply a radical by itself, I get what's in the radical. In other words, we've done this all the time. If I had square root of 3 times square root of 3, I didn't have to do 9, and the square root of 9 is 3. I know it's 3. The square root of 151 times the square root of 151. I don't have to do any work. I know it has to be 151. Anytime you multiply a radical by itself, you just get what's inside the radical. So if I'm multiplying the square root of -1 times the square root of -1, I am again multiplying a radical by itself. It's just going to give me -1. And this is probably the most important fact you should know about imaginary numbers. I is the square root of -1. I can't be simplified. But I squared is -1, not in a radical. I squared itself is a real number. It doesn't have a negative inside a radical. So whenever I come across an I squared, I'm going to replace that I squared by -1. I'm going to have to leave, but I squared, I'm going to replace by -1. So now let's see what we have. This -5i squared is really -5 times -1, which becomes +5. So now I can add the like terms. 6 plus 5 gives me 11. And 3i minus 10i is -7i. And this is my answer. Notice it can't be simplified any further. It is in a plus bi form. It is a complex number. So the one thing you have to remember when you're multiplying is if you ever come up with an I squared, don't leave it I squared, but replace the I squared by -1. Otherwise, everything else is like in regular algebra. Here's one for you to try. suppose I ask you to multiply 9 minus 5i times 5 plus 4i. Let's see what you get as an answer there. We have 9 times 5 is 45, that's first. Then we have outer. 9 times 4i is 36i. Notice this is like regular algebra multiplication of binomials. Inner, negative 5i times 5 is minus 25i. And last is negative 5i times 4i, which is negative 20i squared. Don't forget, when you have an I times an I, you get an I squared. And the only thing that's different than regular algebra is this I squared, I know I replace with a negative 1. So this negative 20 times negative 1, you're multiplying. These becomes positive 20. And I can combine the 45 and the 20. Those are regular numbers, regular real numbers. That gives me 65. And the 36i minus the 25i, 36 minus 25 is 11, so that's plus 11i. Notice this is an a plus bi form. The a is 65, the b is 11. It is a complex number. Do not leave your answer with an I squared. Notice you have to write the whole thing. Your final answer is 65 plus 11i. Are we okay with that? Okay, so let's do one more thing. We've learned how to add and subtract and multiply. Let's talk about dividing complex numbers or numbers that have I in them. So if I have something like this, let's say I have 3 plus 2i over 7i. Say I had something like that, where I have in my denominator a monomial. What we want to do is rationalize the denominator. I is not a rational number. I is really a radical. It's a square root of negative 1. And we never want to leave an I in the denominator of a fraction. And if you recall, what we do is, depending on whether my denominator is a binomial or a monomial. If it's a monomial, as in this case, the only problem is this I. What am I going to do with the I? I'm going to multiply both the top and the bottom of this fraction by I. Because then I'll get an I squared, which I can replace with a negative 1. It's just like if this would be a square root of 2, I would multiply the top and bottom by square root of 2. So I'm multiplying the the numerator and denominator by I. Now let's do the denominator first. 7i times I is 7i squared. And remember, I squared is negative 1. So my denominator comes out to be negative 7. What about the numerator? Well, the numerator I have to multiply using the distributive property. So 3 times I will give me 3i. And 2i times I will give me 2i squared. And again, I see that I squared, I have to make that a negative 1. So what I'm left with over here, let's see what we're left with. It's 3i. 2 times negative 1 is negative 2, because I squared was a negative 1, over negative 7. Now, what we usually do with these type of things is that we separate them. We write them as two separate fractions. In other words, we write this as 3i over negative 7 minus 2 over negative 7. Now, when there's a negative in the denominator, we generally bring it up front. So this becomes negative 3i over 7. And here's a negative, or a negative becomes a positive, which is 2 over 7. And the two, if we want it in what we call a plus bi form, we have to put the number, the 2 over 7 first, minus 3i over 7 second, because we want the real number first and the I number second. This would be the proper way to write in what we call A plus BI form. So what we do with our final thing to simplify it, we separate both terms and put them over the negative 7 individually. Now, what would happen? So I'm going to do one other problem and then I'll let you go. What would happen if you had a binomial in the denominator? What if I had something like this? Suppose I had a complex number 5 plus 2i over 3 minus 4i. A complex number, this looks like we're dividing a complex number by a complex number. But what we want to do really, even though it says divide or it says simplify, we want to make sure that we rationalize the denominator. We want to make sure, just remember this I is like a radical. We don't want a radical in our denominator. But the problem here is that my denominator is not a single term. It happens to be a binomial. But it works just like what we did with the radicals. Remember what we did when we had a radical in the denominator with a binomial? We multiplied by the conjugate. We're going to do the exact same thing here. The conjugate of the denominator will be 3 plus 4i. You'll see that when we multiply a binomial, a complex number by its conjugate complex number, we're going to end up without any i's in our expression at all. So we're going to multiply by the conjugate of 3 minus 4i, which is 3 plus 4i, in both the numerator and the denominator. Now, let's think about this. Doing the denominator first, I'm multiplying conjugates. And when I multiply conjugates, I don't have to do the whole FOIL. I just do first and last. So I'll do 3 times 3, which is 9. And negative 4i times positive 4i, which is negative 16i squared. And the I squared is negative 1. So this becomes 9 plus 16, or 25. Notice, by multiplying by the conjugate of the denominator, I end up with a denominator without any I at all. I end up with a rational denominator. But I have to multiply the numerators as well. I have to multiply the 5 plus 2i by the 3 plus 4i. And in order to do that, then I have to use the whole FOIL because they're not conjugates. It's not enough to do first and last. So let's do that. 5 times 3 is 15. Outer is plus 20i. Inner is plus 6i. And finally, last is 2i times 4i, which is 8i squared. Don't forget, the most common error people make is they do I times I and they just write I times I is I squared, and then I squared, remember, when I see it's equal to -1. So this is 8 times -1 is -8. So now I have to add the 15 and the -8, which is 7, and the 20i plus the 6i, which is 26i. Now, the better way to write this is to separate it and put each number separately over the 25. So the better way to write this is 7 over 25 plus 26 over 25i, and that's your complex number, which is the answer. That's really the result of dividing 5 plus 2i by 3 minus 4i. Notice we didn't really do division. What we did is we rationalized the denominator by multiplying by the conjugate. I think I'm going to stop right here. Make sure you check your delta math. We're going to start the next class by reviewing this a little bit, and there is going to be, make sure you're current on your delta math. I have extended the delta math deadlines. There's a deadline that's the regular deadline on the delta math, but I've extended all the deadlines, all the due dates for till I think it's December 5th. That if you do it by, if you didn't do it on time, but you did it by December 5th, you'll get 90% of the credit. So if there's some assignments that you haven't gotten to yet, make sure you go back and do them. It's close enough for you to be starting to review for the final. Our final is probably going to be the week of the 14th of December. So we're like 5 to 6 weeks away from the final. So make sure that you keep current. Does anybody have any questions they want to ask me?